Okay, how to make an electrochemical cell. Okay, how to make an electrochemical cell. So we're going to take chemical energy, and instead of making heat energy, instead of letting the chemicals mix together and make heat energy, we're going to turn chemical energy into electrical energy. We're going to measure the voltage. Okay, so how do you do this? How do you make an electrochemical cell? So we're going to just take a very simple example, and we're going to take a beaker. So you're going to have a go at actually doing this experiment. But you take a beaker, and inside the beaker we want standard conditions. So we put copper 2 plus ions, and we put concentration 1 mole per decimeter cubed. So this can just be copper sulfate, concentration 1 mole per decimeter cubed. Right, and we put a strip of copper, solid copper, in the beaker, in the solution, solid copper. Okay, like that. And this is called a half cell. And then we connect it with some crocodile clips, and we connect it to a voltmeter, to measure the voltage. And we have another half cell. So in the other half cell, we're going to put, this is the most simplest example, yeah? We're going to put some zinc ions, zinc 2 plus ions, concentration 1 mole per decimeter cubed, because it's standard conditions. We're going to dip a piece of zinc, solid zinc, in the solution, like that. I'm going to connect it with crocodile clips. We're going to connect it to a voltmeter. Okay, and we're going to make a circuit. Now electrons are going to flow through the external circuit, but we can see here that we've got a gap, so we need to put something. We draw it just like this to close up the gap. Okay, and that's called a salt bridge, to link the two half cells, a salt bridge. Now a salt bridge, very simply, is a piece of filter paper, white filter paper, soaked in potassium nitrate solution. Okay, now the purpose of a salt bridge is that it completes the circuit, by allowing movement of ions, between the half cells, between the two half cells. The electrons do not flow through the salt bridge. Okay, electrons go through the external wires, leads. Electrons do not flow through the salt bridge. Okay, it's just an inert material, doesn't get involved in the actual electrochemistry. Filter paper soaked in potassium nitrate solution. Okay, right now, so when you get a table, you'll be given a table of electrode potential values, right? So something like this, okay, and it gives you the standard electrode potential for each of these half equations, right? So if you get the value for copper, so if you take copper and its value, it's always written, standard electrode potentials are always written as reductions, and the value for copper is 0.34 volts. Okay, 0.34 volts. And the value for zinc, when you get it from the table for zinc, always written as a reduction, because the standard electrode potential, zinc, the standard electrode potential tells you how readily the reduction happens. For zinc, it is minus 0.76 volts. Okay, so that's just taken, you'll be given a table of standard electrode potentials written as half equations, and you just read off the value. Okay, for copper it's 0.34, for zinc it's minus 0.76. The more positive one stays as a reduction. Okay, the more positive one is a reduction, right? So if you connect this to the positive end of the terminal, positive terminal, at this side here, reduction is happening. So at this side, the copper ions are being reduced to copper, right? If the zinc is connected to the negative terminal, then it's this side, oxidation is happening. Oxidation is happening. Loss of electrons, okay? And we know that because this one has a more positive value, so stays in the forward direction. This one has a less positive standard electrode potential, so goes in the reverse direction, okay, less positive. So oxidation is happening here, reduction is happening on this side, and electrons are flowing. The zinc is releasing electrons, and the electrons are flowing from the negative half cell to the positive, and the electrons are coming around here and gaining with the copper ions to make copper. And so it's got a flow of electrons from the negative to the positive. Okay, so if you left this running a long time, the piece of copper will just get bigger and bigger because copper is being made. The piece of zinc would just get smaller and smaller because the zinc is being converted to zinc 2+. Okay, and that's the electrochemical cell. Right, and you can read the voltage. Now, so the overall ionic equation that is happening in this cell. So we've got copper 2+ being reduced. Okay, we've got zinc being oxidized. So the overall ionic equation of what's happening in this overall cell, so that's a half cell, electrochemical cell. If we add them up together, the electrons cancel out. We've got copper 2+ and Zn goes to copper and Zn2+. So that's the overall ionic equation. If we work out the cell potential, it's called the cell potential. Also goes, you can call it the cell voltage. You can also call it the electromotive force. So, and we're just going to write E cell, the cell potential. Then it's we kept that in the forward direction, 0.34. And we turned around, the zinc got turned around. So it's minus 0.76 in that direction, but we turned it around, so it's 0.76, and that comes up with 1.1 volts. So the reading on the voltmeter should be 1.1 volts, and that's the cell potential or the electromotive force. Okay, and that's how you make a electrochemical cell. Right, now, last time we said that if the cell potential is positive, then the reaction is likely to happen in that direction. Okay, but there are limitations to that prediction. Limitations, right? So if the cell potential or the cell voltage, so if the cell potential, cell voltage, is positive, then the reaction should happen as written in that direction. Okay, so this reaction should happen, right? But there are limitations to this prediction. The limitations, right? And the limitations are, this should happen, but the limitations are that if the rate of reaction could be really slow. Yeah, it could be a slower reaction, maybe have a high activation energy. And so no matter that this is a positive, it just might be a very slow reaction, okay? And second, the conditions may not be standard. Okay, so the actual conditions used may be non-standard. Okay, so as a rough guide, we say if the electrode potential, standard electrode potential of the two half cells is greater, differs by more than 0.4 volts, right? So if the standard electrode potential of the two half cells differs by more than 0.4 volts, then the reaction is likely to happen. The reaction is likely to happen. And therefore, if it's less than 0.4 volts, the standard electrode potential of the two half cells, then the reaction is not likely to happen. Okay, but there are limitations. So we don't know anything about the rate. The rate might be too slow, and the actual conditions might be non-standard. So what we mean by this, so let's take this half cell, for example. If we take this half cell, okay, we always write it as a reduction for electrode potentials. Standard electrode potential of this half cell is 0. You don't need to remember this, you're always given these values, right? Positive 0.77 volts. Right. What if this beaker has been left, water has evaporated, it's just been left standing, and this concentration should be, if it's standard conditions, this concentration should be 1 mole per decimeter cubed. But what if it isn't? What if it's actually 1.1 mole per decimeter cubed? Okay, so it's more concentrated, right? So if it's more concentrated, this is an equilibrium. If this is more concentrated, the position of equilibrium will move to the right. Okay, the position of equilibrium will move to the right, and therefore it's going more in the forward direction. This will make this value more positive than what it should be. Okay, so if you have a higher concentration of this, it pushes the equilibrium to the right, and this will be more positive. So if you only have a small difference between two half cells, things like this can make a difference if the concentration is not standard. Remember what the other standard conditions are. So we're talking 298 Kelvin or 25 degrees and pressure 1 atmosphere are the other standard conditions as well. Okay, right, so where does this value actually come from? Okay, this value is standard electrode potential. You don't need to remember them, they're always given to you. Okay, but where does this, you need to know where it comes from, the standard electrode potential. Let's do that next. Okay, so first we need a definition. We need a definition for the standard electrode potential. Okay, first we need a definition for the standard electrode potential. So the standard electrode potential is symbol. Okay, standard electrode potential. The definition is, right, of a half cell. Of a half cell, just for a half cell, is the electromotive force okay, which just basically means the voltage, to be honest. It just means the voltage of a half cell compared with a standard hydrogen half cell. Oops, half. That's a half. It says half cell. Okay, and it's all measured at 298 K, 1 atmosphere, all concentrations 1 mole per decimeter cubed. So the standard electrode potential of a half cell is the electromotive force, the voltage of a half cell compared with a standard hydrogen half cell. Okay, so what this means is that there is a standard out there which is given, the value of 0 volts. The standard hydrogen half cell has a standard electrode potential of 0 volts, and everything is compared to that. So it's a bit like when you're measuring the height of a mountain. So there's your sea level, and then you've got your mountain, and you're measuring the height of your mountain, and it's all done relative to sea level. So we're saying the standard hydrogen half cell has a value of 0, and we're comparing everything to that, or maybe in this direction, we're comparing to the standard hydrogen half cell. Okay, so if you're asked, for example, if you are asked to determine for copper, say, all right, aqueous solid, if you're asked to determine the standard electrode potential of the copper half cell, how do you do it? So you're asked to determine the standard electrode potential of a copper half cell. So the first thing you do, you connect it to a hydrogen half cell. Now a hydrogen half cell, there's different ways to draw it, okay? This is the way I'm going to draw it. Some people say it looks like a duck. Now because hydrogen is a gas, we need a different setup, right? This is just made of glass, right? This is just made of glass. It's just a glass container, right? But what we're going to do is we're going to pump into this glass container, we're going to pump hydrogen gas at 1 atmosphere pressure, all right? And we're going to stand it, in a beaker of H plus acid, all right? Constant H plus acid, yeah? Concentration 1 mole per decimeter cubed, right? So what we're saying is we're going to go from H plus an electron, okay, to hydrogen gas, right? And that has a value of 0 volts, right? Now, if we write it slightly different, if we write it as 2H plus 2 electrons goes to hydrogen gas, right? That's absolutely fine, and the value is still 0 volts, yeah? You can double up, it's absolutely fine. That's the half equation. You can use this one or this one, right? Now, we're going to bubble hydrogen gas. Now, we need a metal, because it's all to do with electrical, so we need a metal. We have a wire coming down, so this is glass, and we're pumping in hydrogen, and we need an inert metal to act as an electrical contact, and the inert piece of metal that we use is platinum. It's a piece of platinum, and it's actually called so the platinum provides an electrical contact, and it's inert, so it doesn't react, okay? And the piece we use is called platinum black, and this is a piece of platinum coated with finely divided platinum. So it's a piece of platinum coated with powdered platinum, finely divided platinum. So it increases the surface area. So there's lots of surface area for contact. So you bubble in your gas, and so let's be like bubble, bubble, bubble coming out like this, yeah? And electrical contact, and it's all done in acid. And the half equation for this half cell is that, and it's given the value 0. And it's like we're just saying that is 0. Let's measure everything else relative to 0. So we need to find the electrode potential of this, all right? So we connect to a voltmeter, and we connect it to the copper half cell. So we put a piece of copper, solid copper, these are the leads, solid copper, and we stand it in a beaker of copper 2 plus, concentration 1 mole per decimeter cubed. Okay, don't forget the salt bridge to to keep this, get the connection, keep the circuit, we need a salt bridge. Okay, now if this is the positive terminal, the positive terminal is where reduction happens. Okay, and this is the negative. If this is plugged into the negative terminal, at this side, what is happening is reduction is happening. Okay, and the electrons are being released. Not reduction, sorry, excuse me. This is where oxidation is happening, and the electrons are being released, and they're traveling through this here, and this is where reduction is happening, and the electrons are being gained. Okay, so this is the positive terminal. The reading on the voltmeter will give the value for this. So we already know for copper, it should come up as 0.34 volts. Okay, positive. So the reading on the voltmeter will be the reading for that. Okay, and that's what you do. So here's another example. Just give you another example. So if you take, let's see, which one should we do? Which example should we take? So if you have, let's go, right, if you go like, if you go silver, we take a piece of silver, solid silver, yeah, and you stand it in silver ions. Silver is 1+, silver ions, concentration 1 mole per decimeter cubed. Right, we try to find the standard electrode potential. We plug it in the positive terminal, and then we connect it to the hydrogen, which is a piece of platinum, stood in some concentration H+, concentration 1 mole per decimeter cubed, that's aqueous. Put the glass kind of vessel to pump the hydrogen in, just done like that. It's in acid, hydrogen gets pumped in, 1 atmosphere, yeah, and it gets pumped in, and that's the negative terminal. And then the reading on the voltmeter will be your actual value for this half, because at this side, if that's the positive terminal, that means, that means that at this side reduction is happening, and at this side it means that oxidation is happening. Okay, and you get the reading on the value, and this would be maybe, I think it's 0.8 volts. Okay, do not forget your salt bridge, which has to dip into the solutions, and has to be labelled to get the marks. Okay, so that's how you find the standard electrode potential of a half cell. Right, but sometimes you've got to check the state symbols, right? So for example, right, if you're asked, for example, to find the standard electrode potential of this reaction, this half reaction, always write them as reduction, and you're asked to find this plus water, 4 waters, okay, right, aqueous, ions are aqueous electrons, and liquid water, right? You need to make sure that in your beaker you have got MnO4 minus, concentration 1 mole per decimeter cubed, that you've got acid, concentration 1 mole per decimeter cubed, that you've got Mn2 plus, all of them 1 mole each 1 mole per decimeter cubed. There is no solid metal, so you have to have a piece of platinum. If there's no solid metal, you will need a piece of platinum, and that's your solution, and all of that is in the beaker. Then you connect to the voltmeter, then you connect it to the hydrogen electrode, then you do the salt bridge, and that's how you set it up. Yeah, it doesn't matter whether you write the hydrogen electrode on the right or the left, it doesn't matter. What's important is whether which terminal it's connected to. Is it connected to the positive? Positive terminal is where reduction is happening because electrons are coming, and the negative terminal is where oxidation is happening. Yeah? All right, one more example. If you take, checking out state symbols again, if you have this reaction, right, if you have, you've got to find chlorine, gas, and electron going to chloride, aqueous, right? And you got to find the electrode potential for that. Got to find it. Then it's gas, right? So your setup on this side is going to need to be the glass jar, like this, because you're going to need to pump in chlorine gas, 1 atmosphere. You're going to need, there's no metal, so you need your platinum electrode. You need it to be sat in chloride, 1 mole per decimeter cubed chloride, aqueous, 1 mole per decimeter cubed. You need your salt bridge. You need the other hydrogen electrode, voltmeter. Then you need the other, oh, my drawing is rubbish, isn't it? And then you go, the hydrogen, you need it on both sides. Let's do some bubbles. It's nice to have a few bubbles. Then you have a solution. Then you got your inert platinum electrode, platinum, and then that's set in H+, and that's got a hydrogen gas going in there, 1 atmosphere. And like that, so you need the gas jar on both sides. Okay, right, and that's it. Just need to practice questions now.